year the theme is complexity and cryptography, and there have already been 3 workshops. Authenticated encryption was, there was a workshop in Kolkata in September, and then Boolean complexity in Gandhinagar in November, complexity and cryptography in Bangalore in January, and I think many of you here have been for the previous workshops. In fact, for me this is the first workshop in this thematic year on arithmetic complexity. So this is a 5-day, 3 days and 2 half-days workshop. And we are a small enough group, so I hope that we can keep everything sufficiently informal. We have a very nice lineup of speakers and talks. Thanks to all the speakers who agreed to come and give these talks here. And I hope that there will be a lot of interaction both during the talks as well as outside the talks. The schedule is not very congested, and that is intentional. We do want to leave a lot of time for discussions of various types. People who are already doing research may want to get going and prove new theorems while at this workshop. That's great publicity for the workshop. And people who are trying to figure out what's going on should have enough time to catch their breath and go over details after the talk is over at leisure. Maybe catch some more senior people to explain to them at length what's going on. So hopefully the schedule does allow time for all of that. In terms of logistics, there are very few announcements that I want to make. Some of you have asked for travel reimbursement, so I hope you have got a travel reimbursement form when you registered. Do hand in the forms by, say, tomorrow evening with whatever attachments. You can hand it over to me or to any of the office staff, and the money will come into your account sometime later. Okay. Today, most of you have been here for lunch, and you saw the place where we had lunch. Every day lunch will be there. During the session, coffee, refreshments will be downstairs. So 3 floors below this, there is another lecture hall, and outside that, there's a kind of foyer. So we need to troop downstairs for tea or coffee and then come back here for the talks. There will be one workshop dinner on Wednesday evening. So on other evenings, you can do whatever you like in town, but keep that one evening free where we can meet more informally here. It's within ILC, but in a different setting. We can socialize it. Okay. For things to do in Chennai, I was wondering whether to put some information in the handout. Then I realized that in this workshop, more than 50% participants are from Chennai. And as Nutan nicely pointed out to me, of the 50% who are not from Chennai, a good 20% or more have some Chennai background. So if you want information on what to do, just find somebody who can tell you that. There are lots of people here who have the right information. Okay, so that's it. Now we're ready to begin the technical part. Our first speaker for today is Nutan Limaye, and she's going to talk about sums of powers of linear forms.
Thank you. Thanks to the organizer for inviting me here and giving me a chance to speak. I'm going to talk about sum of powers of linear forms, and this is a joint discussion which I'm presenting here. So we haven't written anything up. There are some 2 rough drafts, and I would be happy to share them with anybody, but they are in a very rough shape right now. But I'll just present the full proofs, and so it should not be a problem. So the outline for the talk is, I'll just talk about sigma power sigma circuits. So for some of you who have not seen such circuits, I will just give a couple of examples of what I mean by giving bounds for models which compute polynomials using such models. And then I will relate this model with something else that is well studied, which is called the Waring rank. Then using very elementary techniques, basically linear algebra and mathematical deduction, rules of mathematical deduction, we'll just prove some bounds for these quantities I'll define here, and then I'll state a few open problems. Okay, so let me get started. Sum of powers of linear forms. So the way to write such a quantity would be, I take a large sum, and I have some linear forms, and I power them. So this is sum of powers of linear forms. This is the model, and sometimes in arithmetic circuit complexity, this is the notation used for it. The outer big summation stands for the big summation written on the board. This symbol is like a product, a special product, which whatever feeds into it takes powers of that. And the lowest level summation is basically the linear form. What do I mean by a linear form? A linear form could be a quantity which looks like this. Okay, so it's just sum of variables with some coefficient. So, we are assuming homogeneous linear forms here, there is no affine term here. This assumption is not necessary for all our purposes, but I am just assuming this will be without loss of generality for whatever I speak about. Okay. So, this is the model of computation, and this is a very well studied model even in arithmetic circuit complexity, where one very interesting example is known for computing something using this model. So, imagine, so what is an arithmetic, so what is a polynomial? Polynomial is just a sum of monomials, right? And suppose the base element in every polynomial is a monomial, and suppose I were to compute a monomial using this model. So, then maybe I can build up more things from there. So, suppose my problem is very simple, I just have to compute the following monomial. This is just a product of n elements, and I want to compute it using this model. Okay, so I have to somehow come up with the right alpha i's, and I have to come up with the right combinations of these, and then power them appropriately so as to obtain x1 to xn. Okay, and this was done, such a computation was done by Fisher, and I am going to just give a simple slightly different variant of how to compute this using sum of powers of linear forms. And that is a technique all of you would have seen if you have done a basic course in discrete math. This is just inclusion exclusion principle. So, just using inclusion and exclusion principle, how do I compute this? Well, I start with something like this. Now, this computes x1, x2, etc. up to xn, that monomial, but many other things. So, I try to cancel off the other things from this part. Okay, so, let me do that. Let's take subsets of n which are of size n minus 1, and let me do this. Okay, but now I have subtracted too much, so I add back a few things into this. And so on. Okay. So, once I write this entire thing down, there will be cancellation, and exactly the way you kind of build a certain subset using this inclusion exclusion principle, you will be able to see that this computes nothing but n factorial some coefficient times the monomial of our interest. Okay. And that coefficient is just dependent on n here. Okay, so, this is from first principles, this construction is known, and now this actually looks like a circuit like this, right. These big summations, I can sort of club them together with these minus, pluses and so on, or I can push them inside, whatever you like, but it can be written down in this format, where I take some linear forms, raise it to some powers, and then just do some cancellations across terms. Okay, so, I have not worked out the full details here, but maybe it is not a very difficult exercise maybe to just work it out and expand this whole thing out and just say that the two terms are equal, two sides are equal. Okay. So, this is Fisher's construction, and here the size of S, because I am doing this for every subset, it turns out that this construction is going to say that S is equal to, for this construction I am saying, the S turns out to be 2 to the n. Okay. So, this is a very, very simple construction, but by using some slightly difficult or slightly different techniques, you can improve this 2 to the n upper bound to 2 to the n minus 1. Okay, and Fisher had already done it in his paper. He had proved that if I were to compute just the monomial x1 to xn in this model, then in fact s equals 2 to the n minus 1 suffices. Okay. So, which Fisher is this?
When was this done?
80s, I'm not sure. Yeah. I'm not sure about the affiliation. You know the Fisher?
I Fisher. But this particular construction, I guess, is like essentially Rice's formula.
Yeah, this is Rice's. This one is Rice's, but 2 to the n minus 1 probably was Fisher.
Some I Fisher, I don't know the person.
Oh, you mean the, I thought that was the name. Okay, I dot Fisher. Okay. Okay, I don't know the person, I mean, who it is. Not sure. So let me just write that down. So Fisher proved that, let's call this monomial something. M can be computed with now, well, one question would be, is this tight? And in circuit complexity, there are results which don't exactly prove the tightness of this result, but show a pretty good lower bound. Okay. So let me remind you of something that some of you may have already seen, which is a lower bound. So by examples I meant, so this is one example of a polynomial which can be computed in this model. And now another example I want to give is sort of a lower bound example, if you wish, that if I were to compute a polynomial in this model, then I must require size so and so. Okay, so and it is, I'm going to use the same example polynomial, which is the monomial, and let me say that you can actually prove a very almost this tight lower bound, okay, by the techniques we know. Okay, the technique. Exactly. Yeah, exactly. So, yeah. So why did it's in some sense to prove the power of a certain model, it's nice to be able to compute a monomial in it for arithmetic circuits, because then you are sure that given enough number of gates, you can compute any polynomial, because a polynomial is nothing but a sum of monomials. So it may not be the best representation for a polynomial, but of course you can compute it. In that sense, it's a universal model. Once I show you that a monomial can be computed in this model, you know it is universal. Now for the lower bound. So for the lower bound, I will have to introduce something. So let me just ask, has some of, so how many of you know partial derivatives or methods in arithmetic circuit complexity? So just to get an idea as to how detailed I have to be. So okay, fine. So let me just quickly recap a couple of things. So here is a very simple outline. If I were to prove that a certain model requires at least so much size to compute a polynomial, this is one outline proof that you can try to fill in. Usually filling in is difficult, but what you can do is you can define a measure from some polynomials to real numbers or good enough, some space, integers, real numbers or whatever, and prove that mu for this model, say, is small. Let's call that small something, say capital S, and prove that mu of m is large. If you are able to fill in these two details and come up with a mu like this, then essentially you have proved a lower bound for computing m in this model. because any m computing it has small measure, but the monomial has a large measure. So if this model alleges to compute this monomial, it should be of large size. So we'll try to do this proof very quickly by defining such a measure. And the measure we will use is so partial derivatives as a mathematical object, I'm sure all of you have seen. So that's what I'm going to use. What I'll do is I will take any polynomial f, and I'll try to take, I'll take derivatives of this polynomial. So let me say that the polynomial f is, say, on n variables and of degree n for now, because that's how our polynomial is anyway. So let's say it is like this. So I take derivatives of this with respect to subsets of variables, and I say that these subsets are of size n by 2. Let's call this set something. Okay, and my mu for a polynomial, so p of f, say, will be just the dimension of this. So what do I mean by dimension? Well, this gives me a set of polynomials, and they are sitting inside, you can think of them as sitting inside a vector space. Okay, and now I just compute the dimension of that vector space. So now mu f is just this. Okay. Now if this is my mu, let me try to analyze both these things under that mu. Okay, so fine. One of them is easy to do. I claim this is at most little s if little s is the top fan-in. Why is that? Because I am taking n by 2 derivatives. So what is happening to my monomial? Suppose I take the first subset of n by 2 variables, I take derivatives with that, I am left with the last subset. So every subset I choose, the complement of that set is with me. So that's the action on the monomial. What happens to this model here? What happens here is, firstly, a couple of things, because this is a you can see that mu is actually it's subadditive. So this is something okay, let me just use this. Okay, so this measure mu has the property that because proving that is an exercise. By subadditive, this is what I mean, that if I take sum of two FIs and apply mu to that, then it is at most mu of F1 plus mu of F2. Okay. So using this, I can say that it's S times the mu of the rest. But what is the mu of the rest? Mu of the rest, suppose I take a linear form and I substitute it with a variable y. Then I am taking y to the d, and I am taking one derivative of it of y to the n, and I am taking one derivative of it of degree n by 2. Okay. So that's the effect. By product rule, you can see that basically it gives exactly one contribution of order 1 per product gate here. Okay. So basically you get that not order 1, exactly 1. And this becomes at most S. Okay, if this part was not very clear, let's try to, so this one will be crystal clear, I'm sure. Mu applied to x1 to xn. This is just every possible subset of size n by 2 that arises. Every monomial will arise of support size n by 2. So this is actually equal to And now by that recipe, if this circuit is alleging to compute this monomial, then we get that S must be at least n choose n by 2, which is approximately 2 to the n by square root n, by Stirling's approximation. So that's all. We have this. S is at least this much. Okay, so this is all the basic stuff. Couple of examples about this model. What we got was, by Fisher we have an upper bound of 2 to the n minus 1, and by this measure idea we have a lower bound of 2 to the n by square root n. Okay. These quantities are off only by 1 by square root n factor. So actually we are very close. Upper bound and lower bound are almost the same, except for this 1 by square root n factor. But what if I just for the heck of it decide to dig deeper and ask, what if I want a tight lower bound for this? Can I hope to get a tight lower bound for this? And these are the kind of questions that people in mathematics have been studying. So this is not a new inquiry at all. In fact, exactly the same model, sigma power sigma, has been studied in mathematics. So just a small break from technical stuff, a small brief history of things related to this in mathematics. And this I am just, I read a survey and I made some notes, so I am not an expert here. But the history is pretty interesting. So let me tell you whatever I know. Maybe some people can add more things here. So in long ago, as in mathematics apparently, Waring stated something in his paper without proof. What he said was, any natural number n can be written as sum of say sum of 4 cubes. And he also said that, so just some notation. So suppose I say that n is a1 to the d plus a2 to the d plus a of nd to the d, say, where nd is the smallest number such that n can be written down like this. Then Waring said that, Waring conjectured that for any d, there will be this nd such that any natural number can be written down as a1 to the d, a2 to the d, etc. up to ad to the nd. So there will be this decomposition of any natural number in this way. Okay. And he claimed that, so let me call this g of d be that number. In this case, the smallest number such that I can write smallest number such that for any n, n can be written as gd many dth powers. Then
Exactly GD or
at most gd, I think, at most gd. Right, sorry. GD, yeah. So that's a good question. These AIs also, he conjectured, were in natural numbers. They were also naturals, and what you were expressing was also natural. And without any proof, he wrote down that GD equals 9. G3 equals 9 and G4 equals 19. And then apparently well before this, Diophantus had said that G2 equals 4, and this was some AD, some 200 AD or something like this. So later Lagrange in the same year, so this was conjectured, and this was by Waring. And then, yeah, so Lagrange apparently in 1770 showed that G2 equals 4, and this was a very celebrated result. You know, every natural number can be written down as sum of 4 squares. Much later, in 2008 and 2012, by 2 different people, and I don't know what exactly was the contribution of each one of them, but and Kemper, they solved that in fact G3 equals 9. Okay, so this was 2008 and 12. And intermediately in 1986, 3 number theorists, so this becomes like a problem in number theory, I think. Balu, who was the ex-director of this institute, with Dress and I think this is a French name, so I hope I pronounce it right, Deschoulier. So all the problems that Waring had stated or conjectured or claimed have been shown to be true. All the bounds that Waring conjectured have been shown to be true. And actually for higher things still many things are open, and there is a lot of literature which I am completely unaware of. Yeah.
Is it at least clear that such a GD exists for all T?
So that was one of the parts of the conjecture, that he firstly conjectured that it exists. Now it's not clear. I don't think it is clear, but I think that is now known or something like that. I'm not very sure. Is this known already or? Right? Yeah, so GD is finite is now known, but again I don't know who did that.
You can do +1, +1, +1.
No. That is the fact that GD is independent of n.
Yeah,
I mean that you can get one bound
for all n.
So is there any upper bound? Is upper bound known or is it just?
Yeah, complete upper bounds are known. And exponential can be.
So, but are they tight? The bounds are tight or the upper bounds or something like
I
that?
think type bounds are known only for the first few.
Exactly, this is what even I seem to have understood. Okay, fine. So this is the problem. So this is Waring's way of thinking about natural numbers, and independently people were trying to write additive decompositions of polynomials as well. And one of the Hilbert's problems was that, so which I will not write down, I will just say it. The Hilbert's problem was that can we write any complex polynomial, so polynomial whose coefficients come from complex numbers, can we write it as a sum of squares of rational functions, where the rational functions are supposed to, so there are a couple of things about the property of the polynomial by which, for which we want to write this in this decomposed format. Firstly, it's a complex polynomial, and then it takes non-negative values over reals. So evaluated over reals, it takes non-negative values, and it's a complex polynomial. He conjectured, or that was one of his problems, that can we write it down as a sum of squares of rational functions. And later in 1927, Artin resolved this in affirmative. Artin proved that in fact you can write it down as a sum of squares of rational functions. Meanwhile, the following problem also got some attention and has been studied for a long time, which is what is our model, bringing it back to our model, which is that, let's say f is a polynomial of degree d on n variables, and let me say that the Waring rank of this f, so this is a definition, Waring rank of f is min over all s such that there exists L1 to Ls, which compute F as sum of Li to the D. Okay, so this is back to our model. We have a degree D polynomial, and we want to compute it as a sum of powers of linear forms. And this quantity exactly is studied in mathematics and is called the Waring rank of a polynomial. Now, the Waring rank of the polynomial has also been well studied, and lot of upper bounds, lower bounds have been proved about this. Let me completely fast forward this and tell you what is the current status quo for our favorite polynomial, which is the monomial. For that, the following is known. So, consider a slightly this monomial. Instead of taking powers of 1, I take powers of d. Then it is known that the Waring rank of M is exactly equal to d plus 1 to the n minus 1. And this is a result proved in 2011 by Renestad and Shreya. Okay, we don't know these names at all because the literature is probably completely different. I mean, I don't know it at all. So, sorry. So this is the bound. And if so now just let's look at this, okay. If I put d equal to 1 here, okay, then we actually recover the bound we wanted for our monomial. If I put d equal to 1, this tells me that the Waring rank is in fact 2 to the n minus 1. Okay, so our measure idea right now, we don't know how to push the lower bound further, but in this literature, they have studied for this monomial, they have studied and given a tight lower bound. All right, so this is one great starting point in some sense, because we don't know how to push our lower bounds here, but for this particular example monomial, it is known to be 2 to the n minus 1. Upper bound was by Fisher, and similar upper bound I think was also rediscovered here, and lower bound was proved in this paper. The final tight lower bound apparently is in this paper. Simultaneously, the following monomial was also discussed. That has been discussed in the literature for a while, and recently again a tight lower bound for this was proved. I don't know whether this is visible at the back. Let me read it out. So for a monomial where the degrees of each variable could be different, and it's already this is not a multilinear monomial, that is every variable can appear repeatedly. Here every variable can appear different number of times as well. Then the rank of this is known to be equal to this, and the equality, so this is exactly, so you can recover this bound from this bound. Put all di's equal and you will basically get this back, because this is I going from 2 to n. Yeah.
So the degree of the first variable doesn't matter at all?
Sorry?
The degree of the first variable doesn't matter at all? You have to order it?
Yeah, so that's a good question. I have to say that d1 is smaller than d2. So take the largest di's. Yeah, sorry. So up to variable reordering, take the largest di's, n minus 1 di's, and yeah, thanks. Sorry?
You can remove the largest di. That's what you can say.
No, you can save the lower one. This is, we are talking about the border rank. For border, you save the larger one. Yeah. For the border one, you remove the larger one. That is how that x to the n y becomes.
Here in the Waring rank, you put that Li power d. So that d is the degree. But
Correct.
how do you know that you could not do better with a different d prime
Correct, very good question. So the question is that what if Li to the d, instead of this I put some, d square, then actually you could do better. Firstly, an important thing to note is that when I say, exactly, so when I say Li to the d, okay, so the left hand monomial the monomial I'm computing has degree d, and here also I have degree d. So suppose Li's had a variable, a bunch of n variables and a constant, okay, then using that constant and higher degrees, I could club up and come up with smaller degree monomials from there. It is imaginable. Yeah? For example, I have x plus y plus c, and I take powers to n, but I were only to compute some x to the n minus 1 y, or whatever, n minus 3 y. Then I could get that as a very weird combination of things with this c taken together. But so this is imaginable, that the bounds completely change if you allow for higher degrees. If you allow for higher degrees and don't allow for this constant at all, okay, then it is clear that you cannot do anything, right? You have to compute that polynomial of that degree. So it is.
If a capital F is homogeneous, then you don't care if it's higher degree or not. It doesn't matter.
Correct, correct. So here all along, Waring's problem has, I should say that the original problem, he in fact even says F is homogeneous. Li's are linear forms. Li's have to be homogeneous. I mean, that's why I said that Li's can, without loss of generality, be non-affine, just linear. Because anyway, this degree and this degree is the same. So this was the question. The degrees are different, yes, and higher. And if this polynomial is non-homogeneous, you could do some crazy stuff. That's okay? Okay, so that's for the literature survey. I would like to say one more thing. So this is known now, okay? All this is known. Let me now, so now what are the techniques? Where do these Waring ranks, etc. get studied? From what I could understand, this is usually in algebraic geometry sort of literature, or it gets studied where people, I mean, the following things seem to be something that one needs to study to understand these proofs. One seems to be something called as secant varieties, which is not a very fancy term, but then there is something called as an apolarity lemma, which they use and then prove these things. I don't know any of these things, but from what I could understand, projective geometry and secant varieties are something that one can kind of understand from what we know, probably, or the way we study things. But apolarity lemma is another lemma that they kind of use. One could use that as a black box and try to understand these papers, but well, I don't know how to understand them as of now. So then what am I trying to do here? I'm just going to prove these results using elementary linear algebra. So honestly, I don't know how to explain the original proofs, and it would be nice if somebody who knows those proofs tells me that, well, what you're doing is that. It's just another language, which is very imaginable. But what I'll present will be pure linear algebra and basic mathematical deductions. And I'll directly prove this result, because this result implies this result. And now regarding the contributions, so the thing is actually, this result for exactly this monomial, Shrikant had already proved, and Nikhil, Sai and myself, we used more or less the same proof or with some modifications to bump it up to this one. So that was the thing. The inquiry when Shrikant started proving that with first principles started with the fact that, can we make Fisher's identity tight? Can we prove the tightness of that? And we were completely unaware of this literature at the time. And that time he was able to prove it using just this method. Then we left it for a while. And then last year, 2 years ago, in the workshop that Ramprasad had organized, Michael Forbes gave a very nice talk about border rank and some nice open questions, and that's where we started. We didn't make much progress on that, but we were able to kind of unify these proofs. Okay, so I'll just present the proof completely right now for this. I don't think so. I don't know. Because for determinant, the way they have studied the determinant also in this Waring model.
But there the degrees are much smaller than the number of units, so I guess we can do better.
Yeah, so they were able to do better. I was not sure whether it was because of the degrees. For determinant, they had some results, but they are not tight in this model, from what I understood. And so when you're asking whether this is the worst example for
So in the sense that if I have an n-variant polynomial and I want to find the polynomial that has the largest Waring rank,
okay.
so is this 2 to the n minus 1 for everything? I mean, in some sense, is the monomial like the
I doubt that
extreme
actually,
case?
but I don't have a concrete reasoning why it's not. I mean, with this, for example, you could compute summation xi to the n. I don't know. In one.
You can't do a linear transformation.
Why would that, and this bound is probably not as good as n plus d
Choose d anyway. Yeah, okay. That's another way to say that. Yeah. So, okay. From the measure idea, you are saying we know that it should be like n choose d.
No,
N plus
generic polynomial should
for
require that many degrees. of
random
freedom.
polynomial probably should require n plus d choose d.
Okay, maybe divided by n. Okay.
So now let me start presenting the proof. So you'll have to put up with some details. But let me immediately simplify the problem to start with. I will just do this for 3 variables. Okay, so the polynomial I wish to compute is, and I promise you that the proof scales. So this is just for 3 variables, and I'm going to prove that the rank of this one is k plus 1 times L plus 1. So this is the thing I will prove now, upper bound as well as the lower bound.
Here m is the smallest one.
Yes. So let's fix that as well. It doesn't matter. So let's just say the ordering among k and L I won't even care about. Okay. So hopefully 10 minutes for upper bound, 10 minutes for 5 minutes for lower bound. I don't know. It's going to go a bit haywire. Okay. But let me give the main idea, and then we'll just wave our hands through this. Okay. So I want to write this as let me also say n. Right? This is the model of computation. This is what I wish to do. Let me start with the lower bound, and then if time permits, we'll do the upper bound. Otherwise, I'll just tell you in the break or something. Okay. So now this is the model in which I want to compute it. Let me rephrase a few things here. Okay. Let's look at a single linear form here. Let me call that Li, and let's look at Li to the n. What is Li to the n? Well, inside Li to the n, you have various monomials. Say you have a monomial which looks like x to the p, y to the q, z to the r. And now let's look at the coefficient of such a monomial. So let's look at coefficient of x to the p, x to the p, y to the q, z to the r inside this, inside Li to the n. Well, it is some constant that depends on just PQR. This is the number of times you can generate x to the p, y to the q, z to the r, times ai to the p, bi to the q, ci to the r. Very simple. And
This is only in Li to the n.
it's only in Li to the n. And now we can make a quick observation that in all these Li's, you can assume Ci is just 0, 1. If Ci is not 0, 1, I divide the entire linear form by Ci. If Ci is non-zero and not 0, 1, I divide the entire linear form with Ci. Otherwise, it's anyway 0. Okay, so I'll assume that all these Ci's are in 0, 1. This is without loss of generality. Now, this is your coefficient, and moreover, so let me call this something. So let me call this Vi, and because R is anyway determined by P and Q, P plus Q plus R is N. So let me just call it I comma PQ. So this is the coefficient of x to the P, y to the Q, z to the R in Li to the N. And now let me build this whole vector of Vi's. Note that this is a vector sitting inside CS.
PQ is a pair.
PQ is a pair, yeah. Should I put a comma or something? So VPQ is this. Now note that, what are the properties of this VPQ? If PQ as a pair is not equal to K comma L, okay, but say also I'll assume that or let's take the simpler case first. Let's say for K comma L, let's look at V of K comma L, KL. V of KL, what do we know about it? Well, the following thing. So this coefficient is 1. And now let's take PQ such that it is not equal to KL. There are two possibilities, either P plus Q equals N or P plus Q is strictly less than N. And for both of them, we know that
VIPQ.
yeah, thanks. Yeah, these are 0. That's just from this equation. We want finally that only this guy survives, everything else gets cancelled. Yeah, but equivalently stated, you can also, so let me call this set of equalities as say U prime or V prime, and these set of whatever identities or as V. Okay, then what it means, in other words, is that VKL is linearly independent of V union V prime. Yeah, there is no linear combination of VI's which can result into VKL. Is that okay?
Just to be clear, this
The
V
left-hand
is,
side.
V is a set of vectors.
Okay, sorry. So the vectors which satisfy this is V.
Q's which are in V prime.
Yeah. Sorry. Is it okay if I don't write it, or should I just so could I say it again? Okay, fine. So what I'm saying is, look at all VPQs which satisfy the property that the PQ pair is not equal to KL, but if you add P plus Q, it's N. What are these VPQs? Well, they are essentially those guys which raise AI to the power P, BI to the power Q, and don't take CI into the consideration at all. Okay, such VPQ vectors, they form a set of vectors which I call V prime. Similarly, with this condition that PQ is not equal to KL and the summation is strictly less than N, they form a set of vectors and I call that V. Okay, if I say V prime and V is this, then these quantities are telling us that there is a linear combination of these which is 1 and the linear combination of these which is 0, which essentially means that VKL is linearly independent of the vectors V union V prime. Okay. So if that is the case, so now let us call this something. This is going to be a central, let's call this star. Okay. Now assuming that, so what we said was our sigma pi sigma power sigma model computing this monomial is equivalent to VKL, the vector, being linearly independent of vectors in V and V prime. Right? We just took that quantity, we rewrote it, we deduced these simple things, linear algebraic things from it, and concluded this. So it's a if and only if deduction that we did. We said that, well, whenever this is being computed exactly in this fashion, it better be that VKL defined so is independent of these vectors. And if that is the case, what I'll now say is that in this space of coefficients, I'm going to find a large set of independent vectors. So, let's just take those guys where P is at most K and Q is at most L. Let me call this V tilde. I'll claim that V tilde forms a linearly independent set inside this set of coefficients. Okay, I have not said how to do this, but suppose I am able to say this. Okay, then what will we get? Note that V tilde's cardinality is what we wanted, and each VPQ which is in V tilde, VPQ sits inside this space of C of S. So if I am able to see so many independent vectors inside a space CS, this must imply that S is at least and this will therefore prove it. So now I just need to tell you how to do this. Everybody okay? Great. So now I just have to prove that this is independent. And that's not very difficult to see again, because VPQ, suppose not, these are not independent. Okay, suppose these vectors are not independent, then there is some linear combination of them that becomes 0. So well, if the largest coefficient which is non-zero here happens to be for VKL, then we are done. That's a contradiction, because we saw that VKL by star has to be independent of all other VPQs. Okay, but if VKL turns out to be dependent, we have reached a contradiction. But it may be that the largest non-zero coefficient here is not that of VKL, it is for some Vij. So say, let's take the coefficient, take the Vij on the other side, whose coefficient is such that it is non-zero, and I plus j is the largest such number for which it is non-zero. So then Vij can be written down as with similar quantities. Maybe gamma will become gamma prime because the coefficient of Vij will come and divide it, minus sign, etc. So Vij will become this. But now notice that we can pump up Ij to become equal to KL by multiplying both the sides with certain vectors. Okay. So note that in this set itself, or in our V and V prime, VPQ dot, by dot I mean just coordinate by coordinate I take products. Then 1 0 say is Vp plus 1 Q, and VPQ dot V01 is VP Q plus 1. So I can just bump it up. Okay, I keep bumping this left hand side up till it becomes VKL. So I'll have to bump it up appropriate number of times. Yeah, for Ij to become KL, I have to bump Ij up by K minus I and J by L minus J. But then I can multiply this side also with that. Now note that, so let's do it. P becomes K minus I, V plus K minus I, Q plus L minus J.
So that number CPQR
Yes.
for V10 is 1, is it? It doesn't matter.
So good point. So actually we could have done all this with respect to UIs, where I take Vi and divide it by CPQ.
Ah,
So imagine you are in that world now.
so you're
Because this is talking about linear independence. So by scaling, you are not changing linear independence.
well, the CPQR doesn't depend on I at all.
Oh yeah, anyway it doesn't depend on I.
You can
It's
pull it
common
out.
for, yeah, absolutely, absolutely. Okay, so now I have bumped it up and I claim we are done. Because we have seen another contradiction. Note that Pk minus I, Ql minus J sits inside our set V. So we have found for all such PQ, for all PQ we started out with, this sits inside that set. So we have observed that VKL has been found to be dependent on V, which is a contradiction. That's all. So that's the lower bound proof. Upper bound, I think I have really overshot the time now. I'll give you the vectors which realize this, the A vector, B vector and the C vector which realizes K plus 1, L plus 1. And then if somebody is curious offline, I can just give the proof. So let me write it as a, so A bar is, so what I do is to realize this thing. So okay, what happened here, the take back message probably is just this star expression. Okay, we are able to write computation by this model as a question about finding linear independent vectors. And this is the same idea that we are going to use even for coming up with upper bounds. And for upper bound, what we will say is that A bar is, I'm going to, so I'll give you A bar and B bar vectors and C bar, both sitting in this space. Okay, so that will give you a valid upper bound. And it's going to look like this. Okay, this is one possible solution. You could come up with a totally different solution which realizes the same upper bound. Okay, but the vector A that we found was useful. Let's call this quantity T, where omega 1 is K plus 1th root of unity. And B bar is going to be blocks of length K plus 1, where I repeat another root of unity, which is going to be the L plus 1th root of unity. And these blocks are of K plus 1 length. Sorry. and C bar is just going to be once. This is length T. So I claim that if you put A, B and C as this in this expression, then you will be able to compute x to the k, y to the l, z to the m. And if you were to attempt this proof on your own, another suggestion is that don't try to explicitly figure out BIs. Just try to argue that with these vectors and appropriate definitions of VKL and VPQ, VKL is linearly independent of the set V and V prime. So to fill in the proof, all you have to say is that we have defined AI, BI, CI, that will automatically define VPQ vectors. Claim that, just show that in this definition, VKL is in fact independent of V union V prime, which is not very hard to prove. Again, basic linear algebra will be enough. Okay, so that gives upper and lower bound, and as you can see, this lower bound proof, we didn't use really anything about there being 3 variables. This can scale. This can easily scale. Yeah, it's just messier to write. I'll have to carry around many subscripts, suffixes, and so on.
Where did you use that M was the smallest degree?
Where did I use that? M was the smallest degree.
When you're boosting.
To
You
get
have
the
a
best
lower
lower
bound for every pair. So you have a lower bound of k plus 1, l plus 1 or l plus 1, l plus 1.
So it works for any of them.
It will work for any of them, but this will be the highest. And what else was I going to say? Yeah. So this finishes everything I wanted to say from the first 3 points. Some open questions. Again, maybe I should not write down too much, but one open question which is, I don't know how hard or easy it is, but to prove tightness of risers inequality. So there is a formula that computes the permanent polynomial using sigma pi sigma circuit, not sigma power sigma circuit, and a good upper bound is known, but we don't know whether this computation done through risers is tight or not. So maybe something similar becomes useful there. Another interesting thing is, instead of this rank quantity, there are other variants of this which have been studied. For example, what Ramprasad was mentioning, border rank, or what Michael Forbes in his talk had mentioned, which are called border rank. And for them, very recently, 2016 was when the tight upper bound, lower bounds were obtained, when you are computing it as sigma power sigma circuits, where the lower sigmas could, as coefficients, have power series from epsilon along with coefficients. I'm just, border rank is the Google search you have to do. And there, now tight bounds are known, but it's not clear whether this, so we were trying to use this method to prove similar bounds for that. We have not been able to do that, but it will be nice to have elementary proofs of this. There they use all these other polarity lemmas along with some representation theory, which again we don't, at least I don't understand at all. So it will be nice to have a totally disjoint proof for this, which is linear algebraic or something like that. And of course, one thing that I am personally interested in, can somebody tell me whether this is the same thing that has been done in another language when they prove these bounds in algebraic geometry or whatever that is. So that is of interest to me. But yeah, that's about it.
Are there any questions right now?
What about over finite field if you want to do this?
No, we don't know that at all. Even Fisher,
So I think it's not possible.
yeah,
Like for example, if your characteristic was 2, there's
just not
no hope
true.
of getting xy from just squares of x. So you won't generate any mixed term.
So characteristic
So,
zero
but
is,
using two,
No, but this,
always
I mean the same thing is even for sin.
any other question?